Alright, so hello there again, boys and girls, and welcome to another science video lesson. And in this video lesson, we will going to talk about something or concept related to plate tectonics. So let's unravel this one and let's discover what is this lesson all about on this video. Alright, so in the last video that we have that I have discussed or I have created last time, we discovered how convergent, divergent, and transform plate boundaries work. Alright, so you know that the convergent plate boundaries are the plate boundaries where the plates are moving towards each other, and the divergent plate boundaries are the plate boundaries that move away from each other, and the transform boundaries are boundaries that slide past each other. All right. In this session that we will have today, we will going to talk about something that is related to these three plate boundaries, and that is right. And that is okay. That is testing the plate tectonics model. All right. So how do we know? All right. How do we know that those plate boundaries are valid? All right, and they are working. All right. How do we know that those boundaries are also true? All right. So how do we know that these plate boundaries is the cause of the motion of the continents? All right, on this planet. Okay. So in this lesson, all right, in this lesson or in this video lesson that we will have, we are going to talk about what are the evidences that are used to support the plate tectonics model or the plate tectonics theory. Now, as we all know, in order for a theory to stand the test of time, there must be some sort of evidences that will support it, and it can stand the test of time. All right, those evidence should stand the test of time for the theory to be valid. All right, in the future or in a future to come. All right, so you need to make or you need to support it with some evidences that makes it valid. All right. So in this session, we were going to talk about what are those evidences. All right. So in order to investigate if in science, in order to investigate if something is if you want to prove that something is true, all right, you need to use a process called scientific method. And the scientific method clearly explains how the plate tectonics theory, from a simple fact or from a simple observation, it became a theory like what we know this day. All right. So here it is. Now, the simple scientific method on how the plate tectonic theory was developed. All right, so let's start first with the hypothesis. Before it became an hypothesis, there is someone. All right, there is someone who observed who observed the geologic processes in nature and conducted some investigation in nature of mountains, all right, some fault lines and other things like related to that. And this person formulated a hypothesis that states that all the continents that we know today doesn't or it is not in their it is not their original position. It came a long way. It came a long way before they go to their present position that they are right now. Okay, so we called it the continental drift hypothesis. All right, so that man will be a topic for another day. So, but for now, let's not reveal who he is for now. All right, so that is the continental drift hypothesis. So that is a hypothesis. It is not during the time that it was released, it was not entertained by the scientific community due to some evidences. All right, due to some lack of evidences that this hypothesis is not present. All right, so that is the hypothesis. Next is After 100 years, there are some geologists who conducted an investigation, and some conducted an experiment on this particular idea, and one of those is the use of sonar in mapping the ocean floor. All right, so if you remember the video, all right, if you remember the video that we had last time about Maritarp and Hisen, yan. So Tarp and Hisen formulated a map of the ocean floor, and they correlate the presence of these earthquakes, volcanoes, and mountain ranges in connection with the plate boundaries. And they found out that they are related to each other. So it gives light. Alright, so it gives light to your continental drift hypothesis that we have right over there. Alright, so because of that, because of those investigations about this thing that are found in the ocean floor, it gives rise now from continental drift hypothesis, it became now your plate tectonics theory that we all know. Alright, now, the plate tectonics theory right now is being supported by some other theories like the one that we have here. We called it the seafloor spreading theory. Alright, the seafloor spreading theory, which we will go over it later. And after the development of the plate tectonics theory, there are a lot of experiment and investigations that underwent in order to support this plate tectonics theory, to make it more valid. Alright, to make it more valid and to further explain what are those geologic processes that are related to this particular idea. Alright, so that is why after the development of the plate tectonics theory, a lot of geologists conducted an experiment in different regions of this planet just to support this idea. Alright, so let's start with the first support coming from the seafloor spreading theory from its proponent, Harry Hess and Robert Dietz. Alright, so these two people that we have right here work hand in hand together in order to support the plate tectonics theory with their own theory, which is called the seafloor spreading. So what do they mean by seafloor spreading? The idea was these large slabs that are found in the ocean floor is said to be moving away from each other. All right. So their idea that this large slab of lithosphere, this lithosphere that are found in the ocean floor is said to be moving away from each other, and while they move away from each other, it carries with them the continents, which also move away from each other. All right, that is what the seafloor spreading theory is all about. Now, the seafloor spreading theory was supported or is supported by the evidence that we have right here. Okay, so the first evidence that we have right here, which is called the ocean drilling. So, okay, so basically, ocean drilling, they drill the ocean and they get some samples from it. Now, this is the most convincing evidence, right, in support of the seafloor spreading theory and also the plate tectonics theory. Now, in this particular evidence, they got data coming, or the data that they got here is the age of the deepest sediment, and the second one is the thickness of the ocean floor. Those are the data that they gathered during the investigation, or the expedition and investigation process. All right. So in this ocean drilling, they use a ship called the Glomar Challenger, and this is a deep sea drilling ship. And the project underwent from 1968 to 1983. All right. So as you can see, this ship is well equipped with a driller. Alright, it is equipped with a drill that is capable of drilling the ocean floor and get some samples on it. So remember, they want to know, alright, so they want to know if the age of the seafloor is the same all throughout, and they want also to know if the thickness of the seafloor is the same all throughout this planet. Okay, and these are the core samples that they gathered during the length of the process. Alright, so and this is the result. Okay, so the result was, alright, the result was, since we are talking about seafloor spreading, we are talking about one type of plate boundary, which is called the divergent plate boundary. Okay, so as we all know, divergent plate boundary is or are the plate boundaries that are moving away from each other. So we have here the ocean ridge at the middle. Right, so we have here the ocean ridge at the middle, and that will be our basis for this for the result. All right, so in terms of thickness, according to the result, as you go far away from the center. So as you go far away from the mid-oceanic ridge, the thickness of the ocean floor increases. Alright? The thickness of the ocean floor increases. It's because of one thing. Because of the pushing force. Alright? So because of the pushing force that comes from the ridge itself, it accumulates material. It accumulates the material as it goes farther away from it. So, it accumulates more and more material, more and more layer above another layer, above one another. And as it goes far away from the mid-oceanic ridge, it became more thicker. It became thicker, something like that. All right, so not more thicker. Okay, sorry. So that is the thickness. Okay, so remember the thickness increases as you go far away from the mid-oceanic ridge. All right, next one. How about the age? The age is also the same thing. As you move away from the center, which is the mid-oceanic ridge, the age of the seafloor increases. Alright, so the age of the seafloor increases as you move far away from the mid-oceanic ridge. So it validates, alright, it validates that the seafloor it validates that the seafloor is spreading. Alright, it validates that the seafloor is spreading because the thickness and the age of the seafloor are not the same all throughout the seafloor on this planet. Alright, so if it validates that the seafloor is spreading, then therefore, the continents or the lithosphere is truly moving. It validates also the plate tectonics theory. So remember, in the plate tectonics theory, it says that the outer mechanical layer of the Earth, which is the lithosphere, is constantly moving. Now, if the seafloor spreading didn't validate, alright, if the seafloor spreading is not true, then therefore, there should be no relation with regards to the movement of your lithosphere. So the movement of the lithosphere will not be possible if the seafloor spreading is not true. So this is the ocean drilling. This is the result of this on that investigation, and it supports a lot about the plate tectonics theory. All right, so as we speak right now, all right, there are a lot of initiatives that is ongoing in terms of investigating further the ocean floor. All right, so we have here the Integrated Ocean Drilling Program, and it started on 2003, and they mainly study the ocean floor and the effects of climate change in the ocean life, all right, and the effects of climate change in the characteristics or the chemical composition of the water, and so on and then so forth. All right, and one of those objective is to drill down the oceanic crust. Alright? To drill down the oceanic crust and probably reach the mantle to get some mantle sample of mantle material for further study. Alright? So the purpose of that one is to study this mantle material, and probably we will now be able to investigate how earthquake behave or how earthquake waves behave, and probably in the future, if possible, we can now somehow predict, all right? We can now somehow predict when the earthquake will happen because of these materials that we will get from the mantle. All right, so these are the places that they went, and they completed their research on those places. And all right, so integrated ocean drilling program is a very ambitious. It's an ambitious project, but the results are very useful in supporting the plate tectonics theory. Alright, so that was the evidence number 1, ocean drilling. Alright, next is the evidence number 2, which is called the hotspot and mantle plumes. Alright, so there are three ways, alright, there are three ways you can produce a volcano, or there are three places where you can find a volcano. Number one is in the subduction zone. Alright, number 2, volcanoes are found in the ridges or rift valleys. Alright? And the third one is the hotspot volcanoes. Or the volcanoes will likely to form in a hotspot. Alright, so these are the three ways that you can produce these are the places where you can find a volcano. Now, hotspot is different from the two that I said earlier. Because hotspot are volcanoes that are not located on plate boundaries. Alright? These are volcanoes that are not located in the plate boundaries. Example of this is the Hawaiian island chain. Very familiar example. Alright, so what are these hotspots? These are caused by rising plume of mantle material. Alright, so these are materials that comes from the mantle, and why do these plumes rise? Because of differences in density. When the material is heated, its density became less or becomes less, and it became more buoyant. Alright, when the material when the material has a lower temperature, alright, when the material has a lower temperature, it becomes denser, and then it sinks down at the bottom. So that's how mantle plume works. Alright, so that's how mantle plume works, and these mantle plumes are somehow upwell. Alright, upwell these hot rocks from the mantle. Alright, from the mantle, to be exact, mantle core boundary. Alright, in their origin. So these rocks that comes from the mantle core boundary, because of the differences in density, it goes up. Okay, it goes up, and once it encounters the part of the lithosphere, the volcanoes can form over them. Alright, now aside from that, these mantle plumes are stationary. Alright, so these mantle plumes are stationary, they are long-lived. Alright, so they do not disappear, they do not move anywhere else. Alright, in the mantle itself. Okay, so it stays in one place. Alright, it stays in one place, and it is continually supplying heat on that particular area. Alright, so to further understand what this hotspot is all about, so let's have this video. Alright, so let's have this video of a demonstration video about hotspot. So how what is a hotspot looks like. Alright, so let's watch this video. Alright, so what's up, my homies? Today we were going to demonstrate how hotspot volcano is formed. So in this demonstration, we need a board paper, a candle, and a lighter. So this is how it's done. Right, so we will place the board paper on top of this candle, like so. Then we will move the board paper as we hover it above the candle. Alright, so as you can see there are black patches that are formed in the board paper as I move the board paper over the candle. Alright, so there you have it. So this is the pattern that we formed after the demonstration. So that's the demonstration on how the hotspot volcano is formed. Let's see each other later. Okay. So that was the demonstration, and in that demonstration, let's put some references on those materials that I used on that process. Okay, let's start first with the candle. So the candle represents the mantle plume because in the video, I didn't move the candle from anywhere else. All right, so I didn't move it. Okay, it stays in one place. The one that I moved is the board paper. So the board paper represents the lithosphere. Alright, so the board paper represents the lithosphere, and the fire on the candle represents the heat coming from this mantle plume. Alright, so the heat that comes from the mantle plume. Again, the candle represents the mantle plume, and it is stationary. The board paper represents the lithosphere, and the fire on the candle represents the heat that comes from the mantle plume. So I hope you did understand what the demonstration is all about. And all right, with that, okay. So what does hotspot volcano look like? All right. Okay, so the hotspot volcano looks like the one that you have over here. Okay, so on top, we have the lithosphere. This one is represented by the board paper that we have earlier. And the rising plume that you have right here is represented by the candle that we have also earlier. Then the heat coming from this plume is the fire on the candle. Now, hotspot is the area, or the hotspot is a place where the mantle plume comes contact with the lithosphere. That is the hotspot. All right. Then eventually, that particular area will give rise to a hotspot volcano. All right. The hotspot volcano is the place where the heat that is coming from the mantle plume will be released. Alright, will be released, and the eruption of the volcano above is the way of releasing this extra heat that is from the mantle plume. Alright, so okay, what is the effect here of the movement of the lithosphere? Alright, when the lithosphere move, alright, when the lithosphere move, in this case, when the lithosphere move, what will happen here is the volcano will be left emptied. Alright, it will be left emptied, and it will go to another place and then creates another opening that you have right here. Now, in some case, when this lithosphere move, when it goes over this particular spot, it will give rise again to another volcano and supply it with mantle materials, and it will be eventually ejected out in a form of volcanic eruption. Alright, so that is how your volcanic hotspot or hotspot volcano is formed. Alright, so based on the demonstration, alright, so the dark and black, or the light and dark patches that you have right here represents the volcanoes that are formed over the hotspot. Alright, so as you notice, there are some patches that are light and there are some patches that are dark. Alright, so the idea is, if it is light, the mantle plume stayed on that particular area for a shorter period of time, like the one that I have right here, this one. All right, so it means that the candle that I used earlier, it stayed on this area for a short period of time. Whereas if the patches are dark and large, it means that the candle or the mantle plume stayed on that particular area for a longer period of time. All right. And also, if you notice, the pattern that I formed in this particular demonstration is it looks like this. I started right here and end over here. All right. So this pattern show us that the board paper was moved on this direction. Alright, so this pattern that we have right here tells us that I moved the board paper in this particular direction, U shape. So speaking common sense, alright, if you move the board paper in a straight line, so therefore the pattern that it will form is also a straight line. Alright? So in reality, if the movement of the plate is a straight line, then therefore the pattern of volcanoes above the lithosphere will be also following that straight line motion. That's how these hotspots form. All right. So if you put this one into the Hawaiian island, all right, the larger island that you have here on the Hawaii is the place or is the present location of the mantle plume right now. All right? So because it is larger than the other islands nearby. All right? So these islands that you have over here are doesn't have any mantle plume at all, and no volcanoes that will erupt on this particular area. So this area that we have right here, this is particularly active. Alright, volcanoes in this area or volcano in this area are active because it is continually supplied by the materials coming from the mantle plume. Now, the question here is, alright, so you can pause the video if you want to. The question here is, how will you measure the plate speed or the speed of the movement of your plate using the islands that you have right here. Alright? That will support the plate tectonics theory. Remember, again, the plate tectonics theory states that the outer mechanical layer of the Earth is constantly moving. So, how will you use this island in order to somehow compute the rate of motion of your plate? So you can write it down in the comment section below. So you can pause this one if you want to. All right. So the second question is it possible to use the island? All right. Is it possible to use the island to showcase the direction of movement of the plate? So we are talking about direction. So can this island tell us the direction of the movement of your Pacific plate in which this island is seated on? Alright, so is it possible? If that is possible, how? Alright, so how to use this island as a reference? Okay, you can pause this video and then write your put your comments or put your answer in the comment section below this video. Now, how to use this island as the reference for the movement or the rate of movement of your plates? Now, you can use the age of the island as time. Alright? You can use the age of the island as time. And over it, alright, above it, okay, so you can have the distance from this island, and you can measure the distance of this island to this island. And okay, and the data that you will gather right there will be the distance. Alright? And using the distance over time formula, you can now compute the velocity or the speed or the rate of movement, the rate of plate movement done by this by the plate in which these islands are seated on. Alright, so using this particular formula. So again, the distance is the distance between the old island and the newest island. And the time will be the age of the islands that you have over here. The average age of the islands that is formed in the process. Okay, so we can now compute the rate of movement. So this is the rate of movement. Okay, so now, how about the direction? Can we use this island in predicting or in showcasing the direction of motion? Yes. All right. We can also use this one. So, the islands that you have right here are only 4 of the many islands that you have in this picture. All right. So this is the present. Okay. This is the island that you have right here. This is the as of now, that is the end part, and this is the starting point of this group of islands that comprises the Hawaiian Islands, or which we call them as Emperor Seamount. All right, so Emperor Seamount. Okay, so by just looking at this picture, we can say that the Pacific Plate, this thing over here, the Pacific Plate, is moving at a northwest format, in a northwest direction. So because this one is going right there, northwest. Okay? So the direction of motion, alright, the direction of motion of the Pacific Plate is going to the northwest of the Aleutian Trench. Alright? So technically speaking, we can use the Hawaiian Islands to compute the to find out the direction and the rate of motion of the plate that you have right there. All right. So, in short, hotspot volcanoes supports the idea of plate tectonics theory. Because of one thing, if all right, because of one thing, if plate tectonics or if lithosphere doesn't move, there will be no group of islands that you have right here, group of islands and some seamounts that will be formed over here if the plates are not moving. All right, so that is the hotspot volcanoes. And as I discussed earlier, so you can use the age and the distance between those islands to compute the rate of movement. All right. Not only that. All right. Not only Hawaiian Islands are the only hotspot here on Earth. There are some hotspot. All right. There are some hotspot here on Earth. There are some places here on Earth that are considered hotspot aside from Hawaiian Islands, and you can go to this website. All right. So you can go to this website to check out what are those hotspots that we have. Okay. So okay, upon looking at it, there are so many hotspots that you have right here. So some of them are being degraded away. There are some of them that are still present at this point in time. So you can visit this website and click on those hotspots if you want to know more about this thing that we have right here. All right, so again, evidence number 2, hotspot supports the plate tectonics theory. All right, so next. All right, so the third evidence is the paleomagnetism. Okay, so among the 3 evidences, this is the most persuasive. All right, so meaning to say this is the most comprehensive. All right, this is the most comprehensive evidence. Why? Because there are a lot of things that this particular evidences can show us, especially the location, the original location of the continent. All right, the original location of that particular place long time or million years ago. All right, so that is why it is the most persuasive, it is the most comprehensive. It contains a lot of data. It contains a lot of data that can support the plate tectonics theory in the future. All right, so ancient magnetism, that's why it is called paleomagnetism. Paleo means ancient, and magnetism is, magnets, something like that, magnetic. All right. Magnetic rocks are preserved. All right. So there are some particles in the rocks that are preserved on it that reacts to the magnetic field of the Earth. All right, that reacts to the magnetic field, or that is sensitive to the magnetic field of the Earth. Now, what this record shows, what this evidence shows is that number 1, polar wandering. All right, so polar wandering. So this is the evidence. The polar wandering is the evidence that the continents move. They do not stay on one place. All right, just like what we have right now on our world map. These are not their original location. Because of polar wandering idea, it gives us an idea that these continents moved from their original position down to its present position. Next is the magnetic field reversal. Over the course of time, there are a lot of magnetic field reversals that happened here on Earth. And this data can be used to support the plate tectonics theory. And these data are recorded in rocks. The good thing here is that they are recorded in rocks. They are not erased. Okay? As long that these magnetic particles are present on these rocks, we can gather data on how or what does this planet look like million years ago. All right. So this is the magnetic field of the Earth, and you know that we have here the North Geographic Pole. This is where Santa Claus lives, right? Something like that. Or rather, polar bear, rather. Yeah. All right. So polar bear. This is the place where we can find polar bears in the North Geographic Pole, the Arctic, the Greenland, some parts of Russia, Alaska. Yan. So these are the geographic North Pole, and the South Geographic Pole is where the emperor penguin lives, the Antarctic. All right. Now, it is different from magnetic pole. So, what we have right here is the south magnetic pole. All right. That is literally the magnet. All right. The magnet part. And the north magnetic pole is the north part of the magnet. So, the Earth is a giant. The Earth is a giant magnet, and this magnetic field originates from the outer core, because the outer core is the only dynamic object in the Earth's interior. Alright, the outer core is the only dynamic object in the Earth's interior. And this the molten iron and nickel produces this magnetic field, alright, that we have right here. Remember, moving charges creates magnetic field. And this magnetic field is very important. It protects us from harmful, deadly radiation from the sun. Alright, so that is the Earth's magnetic field. And on rocks, there are what they call magnetite, right? And this magnetite, as I've said earlier, it is very sensitive to Earth's magnetic field. Okay, when they are in liquid form, they follow this Earth's magnetic field, and then when they solidify, like the one that you have right here, when they solidify, these orientations are stuck forever on this particular rock. Okay, so that is why it is a very good source of data in terms of studying the plate tectonics. All right, so okay, so that is how that is what the magnetite is all about. And okay, let's go discuss what is this apparent polar wandering and how this idea supports that the continent is moving. So first, let's define first what is the word apparent. Apparent means, all right, apparent means what is convincing right now, but not literally true. All right, so what is convincing right now, but not literally true. So, all right, so these are some situations in which what you see that you think is right, but it is not necessarily true. All right, so like the one that you have right here. In this idea, why is it called apparent polar wandering? So the polar means the pole. So we will going to use here the pole, the north magnetic pole to be exact. So this is the north magnetic pole. All right, and wandering means moving from one place to another. All right, so the idea was that it is the north magnetic pole is the one that is moving. All right, relative to the position, all right, relative to the position of your continent. All right, so that makes it apparent. But in reality, it is the land that is moving, not the pole itself. All right, not the north magnetic pole. Okay, so why is it like that? Because if you are standing on land, right? If you are standing on this piece of land that you have right here, you will have the perception that the poles are moving based on the data, based on the magnetic records that are recorded on the rocks per layer. All right, you will have the perception that the North Pole is moving. But it is not. It is the land that is moving relative to the position of your North Pole. Alright, so that is why it is called apparent polar wandering. From the word itself, apparent, you thought that the North Pole is moving, but it is not. It is the land itself that is moving. Now, this is a very good evidence that will support that continents move from one place to another. Alright. So, next. Okay, so what we have right here. Okay, so a simple discussion about this apparent polar wandering. So, 200 million years ago, the land or the magnetite pointed, or the magnetite that are found on rocks pointed to one common North Pole. And eventually, the ridge separates those land that we have right here, one from the western side and one from the eastern side. Alright, so from the, okay, so the new magnetite, alright, so the new magnetite that you have right here, the new magnetite that you have right there, points to the, okay, this new magnetite that you have right here points to the present North Pole that you have on the present, on right now. All right. So the same way the magnetite did on the eastern side. All right. So in this case, we have now 1, 2 North Pole on the western side, and also we have 1, 2 North Poles on the eastern side. So you will you will have an idea that the North Pole is the one moving. All right. You will have the notion that the pole are moving because originally this is the original position of the pole, and presently this is now the position of your North Pole. But it is still the same North Pole. It is only the land where where you are standing is the one that is moving, not the pole itself. Alright, so the pole itself, this pole that you have right here and the pole that you have right now, the one at the middle, is the same. Alright, is the same thing. So it didn't shift. Alright, as well as the one that is on the eastern side. So the pole here that was recorded 200 million years ago is the same as the present pole that you have over here. It didn't shift. Alright, so the perception gave you that the pole are shifting, but it is not. Okay, that is the apparent polar wandering. Alright, so let's go now to the magnetic reversals. Alright, so magnetic reversals are being studied by Fred Vine and Drummond Matthews. Alright, so how did they conduct this investigation? They use what they called a magnetometer. They use a magnetometer, and this device are very sensitive to magnetic anomalies under, even though it is embedded on rocks. Alright, so they can detect these instruments can detect these magnetic anomalies found in the ocean floor. Alright, so they tag this magnetometer in the Atlantic Ocean and in the Pacific Ocean. They also tagged this one, and they found out something more profound on it. At first, they thought there was no magnetic field reversal. Alright? But after the investigation, alright, they found out that there are a lot of times that the Earth's magnetic field reversed in different ways. Alright, so the one on this graph, the one on top is the normal polarity, which I will going to show you what is this normal polarity all about, and the one below, which is called the reverse polarity. Alright, so that is reverse polarity. So on the rocks, it is indicated by the green and white, or rather the red and white color that you have right here. White are for normal polarity, and the red are for reverse polarity. Alright, so there are some, the thickness of this polarity varies. Alright, so the thickness of the polarities varies. For example, if the normal polarity is as thick as this one, it tells us that the normal polarity stayed for a longer period of time before it reversed. The one that you have right here. Now, if the normal polarity is somehow thin, like the one that you have over here, this example. If the normal polarity is thin, it tells us that the normal polarity stayed for a shorter period of time and it changed back to reverse polarity. Okay, so that is the trend here. Okay, same way as the reverse polarity. If it is thick, it stays longer. And if it is thin, like the one that you have right here, it stays, the reverse polarity stays shorter and it changed back again to normal polarity. Alright, so these are the magnetic anomalies. Alright, now, what is the importance of studying this one? The importance of this is to give us an idea when and how long this magnetic reversal happens. Alright, when will it happen? How long it will happen? That is an important data for us to prepare, especially our electronic equipments, to sudden weakening of Earth's magnetic field. Alright? There are some cases when the Earth's magnetic field weaken, it is affected by the particles that are coming from, or the instruments that we are using right now are affected by the particles that comes from the solar radiation. Alright? So from the solar radiation. So okay, in order to give us an idea about how this magnetic reversal happens, this study was conducted. Alright, by Fred Vine and Drummond Matthews. Alright, so what is this magnetic reversal? Okay, so remember the North Geographic Pole, the South Geographic Pole, the North Magnetic Pole. Now, if the North Magnetic Pole is aligned to the North Geographic Pole, then therefore, that is a normal polarity. The South also is aligned with the South Geographic Pole, is also a normal polarity. That is an indication that it is a normal polarity. Now, if otherwise, the South, alright, so if the South is aligned with the North Geographic Pole, then therefore, what we have right here is a reverse polarity. If the North Magnetic Pole is aligned with the South Geographic Pole, then therefore, again, that is a reverse polarity. Alright. So the blue ones, right? As the magnetic field of the Earth changes, as the magnetic field of the Earth reverses, it weakens some of its magnetic field on some places here on Earth, like the one that we have right here. Blue one indicates weak magnetic field, and red ones indicates the strong magnetic field. Alright, so it weakens and it goes back again to its original strength once the reverse process is completed. Alright, so it happens every 100 years, I think, or 200 or 500 years. Alright, so there are some variations in the magnetic field reversal. Okay. Now, how are these magnetic field reversals are being studied? Alright, so as we all know, these arrows that you have right here, these are magnetite particles. As we all know that magnetite is very sensitive to Earth's magnetic field. And, alright, when a volcano erupts, it produces a lava. And the lava is liquid. Alright, the lava is somehow liquid in terms of its consistency. So the magnetite, excuse me, the magnetite on that particular lava is free to move. Right? It is free to move because it is somehow in liquid consistency. It is free to move. If the magnetite detects the magnetic field of the Earth is going that way, then it points that way. Alright. Now, the good part is when the lava cools down, when the lava cools down, the magnetite particles that are oriented in this position will be also stuck on that position. Alright? It will not change anymore. Alright? Once the lava solidified. So that is the reason why you will have different orientation of magnetite over here. Okay? So that is how it's done. Okay? So that is a good thing over here. The magnetite doesn't move when it is solidified in the lava. All right? When it becomes solid, it is stuck in there, and the record or the orientation that it does when it was a liquid will be recorded on the rock itself. All right? So that is how you study paleomagnetism. All right? So these are the magnetic anomalies. So the positive ones are the reverse. Then the negatives are the negatives are the reverse and the positives are the normal polarity. Alright. So it looks like this one. Okay. So in a more realistic mapping of the ocean floor, it looks like this one. The red ones are the reverse polarity that happened in the past, and the white ones are the normal polarity. Alright, so, and as we all know, as we all know, these polarities that you have right here will be possible because of the production of new material coming from the ridge that you have over in this area. Okay, so that is the magnetic field reversal. And as time passes by, the ridge will produce this new material. And this new material will be able to detect where is the orientation of this magnetic field of the Earth. And once it detects that orientation, it will follow that orientation. And once it cools down, it will be stuck in there. Like the one that you have right here, this one. Notice this one. Okay, it will be stuck right there. Okay, and that will be a perfect record on how the magnetic field reversal happened in the Earth in the past million years. Alright, so that is why paleomagnetism is a very good supporting evidence for plate tectonics theory. Alright, so if you were going to ask me if paleomagnetism supports the plate tectonics theory, it will be a hard yes. Okay, so alright, so we go to the last part of the video. How is plate motion measured? Okay, so we have now the evidence that supports the plate tectonics theory. So the question is, how are the plate motion measured? So we discussed earlier that the hotspot can be used to compute for the rate and find out the direction of motion of your plate. Alright, the hotspot. And the second one, since we are in a modern, we can use modern technology to measure the relative motion of the plates. The first one is the very long baseline interferometry. And the second one is the global positioning system. Alright, so I know you are familiar with the global positioning system because on our modern phones, the smartphones, it contains a GPS capability. When you are lost in a particular place, you can use the GPS to verify your location and to help you locate where you are going. Alright, so what is this very long baseline interferometry? This is a very complicated process, but it will use some of the basic trigonometric process or trigonometric formula. Alright, the one that I show you right here is a deep space object. Okay, so how will you use a deep space object? Right, so sorry for that. Alright, so it's deep space object. So this is a quasar. One of the deep space object that we have right here. Quasars emits radio wave. They emit radio waves. And the question here is, you can pause this video if you want to. How can we use this one? How can we use these quasars in order to compute for the rate of the movement of your plate? So how can we use this one to somehow gives us an idea about the rate of movement of a certain plate? Alright, so the radio waves coming from the quasars are being picked up by the radio telescope. Alright, these are radio telescopes. There are a lot of these in United States. Okay, so telescopes. Alright, so radio telescopes. So they pick up these radio waves and okay, so once they pick up these radio waves, they will be able to compute the distance of that deep space object from Earth. Alright, so now here's how it's done. Here's how the very long baseline interferometry works. Alright, suppose the radio telescope is in position on this particular place. This is its original position. Alright, as we all know, the quasar will emit a radio wave and it will be picked up by the radio telescopes. Right? So it will be picked up by the radio telescopes, and what will happen? What if the plate moves? Alright? What if the plate where the radio telescope is standing moves from this position to this position? So this is now the new position of your telescopes. Alright. So the land below it is the new position. Now again, the radio telescope will pick up the radio waves from the quasars. Alright? Now, we have now the second distance. This is your distance 1. and you have your second distance. Alright, so using basic trigonometric formula, you will now be able to compute the rate of movement using the third distance that you have right here, alright, as your reference. Okay, so you have your given distance 2 and you have your given distance 1. Using some trigonometric formula, I don't know if law of sine can be used on here. Okay, I don't know if law of sine can be used here. Okay, so law of sine, if possible, a trigonometric formula like the one that you have right there can be used here on this process that you have right there. Okay, so upon computing, you will get the D3, and using the D3, you will use the velocity formula, distance over time, to compute for the rate of movement of your plates. Alright, next one is the GPS. Alright, there are a lot of satellites out there, okay, revolving or moving around Earth. And these satellites are very good in locating. There are also satellites, there are also receivers that are planted on each of the continent. And geologists always monitor that movement, and that is the reason why they have an idea on how fast each of the plates here on Earth is moving. Okay, some of them are moving greater than 7 centimeters per year. Some of them are very slow, like 1.1 centimeters per year, like the one in the South America Eurasian plate. And there are some that are somehow in medium speed. For example, we have 2.6 to 4.1. That is the Eurasian plate and the African plate convergence over there. All right. So the greatest movement here is 15. All right. So 15, as far as I can see. So there you have it. All right. This is possible because of the GPS receivers that are planted in this continent. All right. They are always adjusted. They are always adjusted every time that the continents are moving. All right, they must be adjusted, because if they are not adjusted, the satellites will not be perfectly aligned to this receiver that are planted in the continents that you have right there. All right, so with that, okay, in order to summarize everything that we have discussed, so the first one, the theory of plate tectonics is supported by the following things. Number one, age and thickness of the sediments that are verified by the ocean drilling. Alright? And also, the ocean drilling supports the seafloor spreading theory, whereas the seafloor spreading theory supports the plate tectonics theory. Alright, the second one are the hotspot. We can use the hotspot volcanoes as frame of reference in tracing the direction, not only the direction, but also the rate of motion of your plate. Alright, that was the hotspot volcano, and the hotspot volcano is possible because of the mantle plume that are stationary below it. Alright. And the third one is the paleomagnetism, the most persuasive evidence that we have right here. Using the ancient magnetism that are preserved on rocks, we can now record the direction and the intensity of this magnetism that happened in the past million years ago. And also have an idea on when and where the magnetic reversal will happen in order for us to give an insight, all right, in order for us to prepare, all right, ourselves to sudden weakening of this magnetic field here on Earth. All right, so these are the things that we have here on this video lesson, and if you did learn something from this lesson, give yourself a high five, everyone. All right, so high five. Okay, high five. Alright, so you did a great job in learning and listening to the lesson that we have right here today. Alright, so with that, hey, that ends up our video lesson for this day, and I hope this thing makes a value to you. Okay, so if this thing is, if you did learn something from this video lesson, just give it a thumbs up on the video, on the thumbs up below this video, okay? And you can comment All right, you can comment and you can suggest a topic that you want me to discuss in the future videos to come. All right. And also, don't forget to subscribe and hit the notification bell on this video. All right, it will help me a lot in terms of the algorithm of this video that we have right here. All right, so I hope you did learn something from this video. Okay, let's see each other to the next science video, everyone. Stay safe and keep on smiling, everyone. So let's see each other next time. Bye, everyone.